In this video, I'm going to show the image of why we need analog-based TX driver in the SerDes system. As we discussed in the Why TX driver video, the output driver in a SerDes is obviously an analog circuit, so that must be an analog-based TX driver. What do we emphasize here? Our purpose here is to clarify the TX driver topology based on how the TX system arrangement and its corresponding advantage and impairments. The system arrangement of the analog-based TX driver is a digital signal after serialization, parallel to serial, that will drive the analog TX driver directly. If there is no FIFO equalization FV or data modulation, there's no difference between it and others, such as the digital to analog converter, DAC-based TX, or segmented-based TX. As we've known, the channel loss introduced the inter-symbol interference ISI, and then the TX must provide the FFE partially equalizing the channel. As we discussed in the Why TX FFE video, the TX input is already in a digital domain, and the digital delay is much easier than the analog delay because a digital delay is just a flip-flop. Since the circuit implementation of the TX FFE would be very simple by adding a few flip-flops without any area or power overhead. Again, multi-delays are added after the digital serialized data, so the FV tap is implemented on the analog driver directly by dividing the whole driver into several elements for each tap proportionally. Here is the case study of an analog-based TX driver with a 2-tap FFE implementation. To make the analog-based FFE image clear, let's define a few things. We'd like to implement a 6 dB de-emphasis along with the first post-pulsar tap and 800 mV output swing. Then we could divide the whole driver under a maximum 800 mV into 8 segments, such that each element would have a 100 mV output swing. Through a super precision and a simple proportional math, we should make the main cursor zero delay as the non-inverted data into a 6 segments or 600 mV subdrivers, and make the post cursor 1 UI delay as the inverted data into the remaining 2 segments or 200 mV subdrivers. Therefore, for consecutive ones or zero long run pattern, the swing would be 400 mV due to the opposite polarity. For a transition, the polarity would be the same due to the 1 UI delay. Therefore, the swing will be a maximum of 800 mV at the data transition. In this case, we will have a maximum swing at the clock pattern high frequency and a minimum swing at the long run pattern low frequency, which matches the inverse of the channel's frequency response and achieve the frequency equation properly. Another standard check of the de-emphasis level is a 400 mV divided by 800 mV, which is 0.5 or minus 6 dB of the swing ratio between the low frequency and high frequency. Another possible topology could be the digital to analog converter DAC-based TX, which makes any encoding or equalization at the digital side or either an FIR or DSP. And the multi-bits DAC is to convert the processed digital signals into an analog waveform. Therefore, the data modulation, FFE, or any digital calibration or processing could be flexible and easy. Also, the DAC only behaves a digital to analog converter without equalization. So the output loading could be smaller than the analog-based TX. If that's the case, why don't we apply the DAC-based TX? Think about the digital limitation images for 5 seconds. Bingo! The digital gates can do much complex digital processing, means the digital circuit is too complicated to operate at a high speed due to the digital timing constraint. In addition, very complicated digital gates operating at a simple rate result more power, even though the speed constraint can be mitigated through a pair processing technique. The total power would be similar and huge. So, the spread over power overhead from the digital gates could be much better than the analog TX driver or the DAC itself. This would be the main reason some people may still want to keep the analog-based TX due to its simple circuit implementation without any power overhead, which would be little design overhead like power, schedule, and resource in the FV implementation. After knowing the DAC-based might not always better than the analog-based TX, let's look at another case study of an analog-based current mode TX driver with a 3-tap FV implementation. With the 3-tap over 2 added delay or flip-flops, the FV configuration is still very flexible to be case 1, 1 precursor tap plus 1 main cursor tap plus 1 post cursor tap. Case 2, 2 precursor taps plus 1 main cursor tap. Case 3, 1 main cursor tap plus 2 post cursor taps. These 3 cases can be implemented easily at the tail current source and the corresponding data inversion. In addition, the tap coefficient can be defined by the tail current source easily with little overhead, since the current source should adjust the output swing even though no FV exists. Lastly, the resolution of the tap coefficient will be also defined by the resolution of the tail current. So, the current mode analog-based TX driver is still very flexible to achieve any FV configuration as the DAC-based TX. Are we missing something? Think about the current dynamic range and then the parasitic images for 5 seconds. Correct. To make a very flexible FV configuration, all the tail current must be able to tune a maximum available current. Since each tap is possible to act as a main cursor tap. Therefore, the output device size of an analog-based TX with the N-tap FV could be N times of the analog-based TX without FV. That's obvious. The TX FV would have a big area and huge loading overhead. The overhead would even make the output capacitance too much, and the TX must equalize itself, not the channel. Therefore, the reduced bandwidth at the output could make the analog-based TX with the FV lose the ability to equalize the channel anymore. Furthermore, the big loading would reduce the impedance at a high frequency. Then, the impedance mismatch at a high frequency not only causes the TX output return loss violates the specification, but also leads to any signal reflection or ring in the time domain. If the self-loading of the analog-based TX with FV is so critical, how can we mitigate the impairments? Think about a simple images for 5 seconds. Bingo! The simpler image always provides fewer overheads. Loss of flexibility means much complexity. To avoid the overhead, we must remove the flexibility and then simplify the FE with constraint taps respectively. Remember, our previous case study of an analog-based TX driver with a two-tap FFE implementation? To avoid self-loading, we will just limit FFE to be two-tap FFE, one main cursor tap and one post cursor tap, for example. Next, the original one, analog-based TX driver with no FFE could be 8 segments to achieve a maximum output swing 800 mV. If we would like to keep the output loading, what could we do? Correct, we must stay with 8 segments, but my fourth 6 segment for the main cursor tap and the 2 segment for the post cursor tap. Think about the trade-off images here for 5 seconds. Right, first, with no FFE, the maximum output swing is reduced to 600 mV. Second, with FFE, the maximum equation or the emphasis level is fixed, such as -6 dB as we discussed, and nothing more. Third, the long-run swing of the main cursor tab and the maximum the emphasis level are trade-offs. Lastly, the fundamental trade-off of analog-based TX driver is between the FFE flexibility and self-loading. Since the advantage of analog-based TX driver is simplicity, most people will give up the FFE flexibility and keep enough output bandwidth. Here are the summarized images of why we need an analog-based TX driver in the SerDes system. Even though the self-loading of the analog-based TX driver with FFE could be a showstopper, most people will keep simplicity by limiting the FFE configurations. In most SerDes, up to 30 dB channel loss at the next rate, the TX FFE might only equalize 3 dB to 6 dB, and the RX CTLE DFE would take care of the rest of 27 dB or 24 dB loss. Therefore, a highly configured FFE at the TX is unnecessary. Also, the FFE's power area overhead of the analog-based TX will be much less than the DAC-based over other TX. So, the analog-based TX driver is still widely used in the high-speed multi-protocol SerDes under high channel loss. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback, and please share your comments down below. Lastly, please share the video link with the people who may be benefiting from it.